Okay, welcome to video class number 19, and we are going to utilize this session for doing some problems. So I have labeled this as numericals 1. That means you will be getting such videos again, but may not be in a scheduled time. Okay, so here is the first question for you. Determine the sensitivity of the overall transfer function of the system shown at omega is equal to 1 radians per second. Okay, so that's it. At omega is equal to 1 radians per second with respect to forward path transfer function. So this is the system that is shown. You know that this is a closed loop system with h is equal to 0.25, and this is your g. This is g of s, and this one is h of s. Okay, and that's a negative feedback system. Okay, now how will you find out the sensitivity? This is a direct question. Hope you might be remembering in the video class 3 we have say, look at this. In video class 3 we studied about the effects of feedback. There we studied one of the important point called as a sensitivity. So we have derived the sensitivity of the system with respect to the forward path gain. This is sensitivity of the gain of an overall system to the variation in G. And that's what the question is asked. Look at this. The question is determine the sensitivity of the overall transfer function at omega is equal to with respect to forward path transfer function. So that means there can be sensitivity with respect to the reverse path as well. So I think I haven't taught you that. I've just only considered the with respect to forward path. So the question is that, and you must also study that from your textbook, or I will be giving you a PDF of that later. So this is actually the sensitivity of the transfer function with respect to the forward path, and is given by, look at this, s suffix g raised to m sm suffix g is equal to 1 by 1 plus dh. So this you have already derived, so that your sensitivity, that is smg, this is what is being asked. So this will be 1 by 1 plus gh, or you can substitute this as 1 by 1 plus 25 by s into s plus 2 into 0.25. Okay, right? Okay, now you can take the LCM over here. Okay, once you take the LCM, you can bring this to the numerator side. So doing all those things, so you may do that for, so that you will be getting an answer like this: s square plus 2s divided by s square plus 2s plus 6.25. Okay, now okay, now this is actually a function of s, and a parameter is given as omega, right? Frequency is given. Do remember, it is not in hertz, it is radians per second, because it is an angular frequency. So this will be s square plus 2s. So in this case, usually in an electrical system or in a system, we put s is equal to j omega, even though we know that s is equal to sigma plus j omega. Since this we are concerned only with the frequency, we can just neglect the value of sigma. We can put simply s is equal to j omega. Putting s is equal to j omega in this equation, you will get this as minus omega square plus 2j omega divided by minus omega square plus 2j omega plus 6.25, and the answer you will be getting. Now what is this omega? Omega is given as 1 radians per second, so you can equate this omega is equal to, so what is omega? Omega is equal to 1 radians per second given in the question. So substituting that, when omega is equal to 1, when you substitute this, you will get the equation, you will get the answer to be minus 1 plus j2 divided by 5.25 plus j2, right? Now, this is sensitivity. Sensitivity is a particular value. I mean, it is only a magnitude. Now, you can find the magnitude of this. You can find the magnitude of this. Now, how will you find the magnitude? This is root of a square plus b square. Here also root of a square plus b square. So, when you evaluate that, so what I meant to say is, so find out this 1 square plus 2 square divided by the magnitude of the denominator will be 5.25 square plus 2 square. Now you may just do it and you will have to get this as 0.398. Okay, so this is the sensitivity of the system. Okay, is it clear? Now another question. Second question, you are given with the overall transfer function of a control system, which is given by 16 divided by s square plus 1.6s plus 16, right? Now you are asked to find the rise time, peak time, maximum overshoot, and steady state error. So we have already found out the relationship for this rise time, okay, rise time, peak time, and maximum overshoot, right? In your video class 14 and 15. So you may just go through that derivation. Now this is just a problem of concerning that. Now before going into that, you should have what is this rise? I mean, before going to the rise time, we know that in a equation of the rise time, so you need the value of theta, right? You need the value of theta, but in the question, no theta value is given. You don't have an idea about theta. Similarly, you don't have an idea about omega n. You don't have an idea about omega d. Now, without this, you cannot proceed with any of these. I mean, say for example, you know what is rise time. Now, the rise time is given by you have already derived it as pi minus phi divided by omega n into root of 1 minus theta square, where phi is equal to tan inverse root of 1 minus theta square by theta, right? This is it, tan inverse theta. But unfortunately, but for this problem, a transfer function is given and we are not aware about theta or omega n. So how will you use this TR? Now, for that purpose, this transfer function is given. Okay. Now, using this transfer function, and it is given that this is a transfer function. And not only that, when you observe this, when you look at this, the transfer function, the denominator of the transfer function, that is s square plus 1.6s plus 16 is actually the denominator, or when you equate this to 0, this is called as the characteristic equation of the second order system. Now, when you analyze the C of s to R of s, what is the general equation for the second order system? That is omega n square plus s square plus 1.6s plus the general equation is omega n square by s square plus 2 theta omega ns plus omega n square, right? Is plus omega n square. Now comparing this general with this general transfer function, you know that this is s square, 2 theta omega ns, that is given as 1.6. Omega n square is 16. In the numerator also you can find an omega n square. So both are the same. So that when you compare this, from this you will be able to get omega n and omega n to be omega n square is 16, or omega n is equal to what? Omega n is equal to root of 16, which is equal to 4, right? So once you found out your omega from that, so you need to do this comparison every time. So you need to be, it has to be comparable with the given transfer function. This is how you should do. So first of all, consider the second order system and compare with this. So from this, you will be able to get the natural frequency of oscillation, that is 4 radians per second. Okay. Now after finding out this, how to find out theta? Now this is of the form s square plus, this is of the form s square plus 2 theta omega ns plus omega n square. So what can you say about this 1.6? This 1.6 is given as 2 theta omega n is 1.6, right? Or what is omega n? Omega n is 4 into 2, 8. So omega n is 1.6 divided by 1.6 divided by 0.8, right? Right. So this is 1.6 divided by, sorry, it is equal to 2 into 4, 8, 8. Okay, sorry. This is 2 into theta, or this is 2 into omega n is 2 into 4, that is right. So this will be point theta. Okay. Now you know the omega n theta to be 0.2. Okay. Now this is theta. So the damping ratio is given as 0.2, while the omega n is this. Now after, if this is known, then you can very well find out TR. Now how will you, TR can be simply substituted as TR is equal to pi minus, okay. Now how to find that tan inverse? Tan inverse root of 1 minus 0.2 square divided by this divided by 0.2, okay, divided the whole divided by omega n is 4 into root of 1 minus 0.2 square. Okay, so you can have a evaluation of this. So tan inverse, okay, this point you need to be a bit careful. So this is pi minus tan inverse root of 1 minus 0.2 square by 0.2. When you take this, you'll be getting that the answer in answer as some 60, 75, or like that. Okay. Okay, so your answer is going to be, if you find this value, you're going to get it is in 78.46, and that is 78.46 degree if you calculate in your degree mod. Now if you do this, if you proceed this pi minus 78.46, the answer you're going to get is wrong. Okay, so that is the wrong answer. So what you need to do is, we have already looked at this, we have substituted something called as omega n, which is in radians per second. So all the degrees will be in terms of radians. This is in degree, this is to be converted to radians, right? So either you may do this problem in the radian mode. Don't forget to switch on to radian mode, and you should know how to convert it into radian and degree, or you may find out the degree, the angle in degree, or angle in degree form, and later convert. If you know manually how to convert a degree to radians, you need to convert it to radians. So this angle here in this type of problems, especially in controlled in this module, you need to be very aware that degree has to be converted to radians. Okay, now converting that to radians, so you need to find out, so your answer is going to be pi minus tan inverse 4.89. okay, so the value of this is going to be 4.89 divided by 4 into 0.98. Now when you take the value of this is going to be 78.46, And if you can find out the find that the value of this in radians and then substitute this. So this is actually very important, that this value should be in radians, and you may be getting in your calculator as 78.46. You need to convert that into radians and then substitute here pi minus that radians, the value of phi in radians divided by 4.98. You will be getting it as 0.45 seconds. Okay, this is TR. Right. Now similarly, what is TP? What is TP? So TP is, we know that this is pi by omega n into root of 1 minus theta square, just as a matter of substitution. That is, omega n is given as 4 radians per second into root of 1 minus zero point 0.2 square. Okay, now you can just evaluate this pi divided by, so there is no need of any, since there is no angle in this equation, no need of any conversion. You can straight away use your calculator and you will be getting this as 0.8 seconds. Okay, now next is, okay, so we have seen the rise time and peak time. Rise time is found out to be 0.4 second and peak time is 0.8 second. Okay, note that peak time is greater than rise time. Okay, so you must remember the second order, the response of the second order system, and in that also you can see that TP is greater than TR. So okay, so this is 0.8 seconds. Now what must be your MP, or what is the next question? That is to find out the maximum overshoot. Now to find out the maximum overshoot, the maximum overshoot is given by MP is equal to e raised to minus theta pi divided by root of 1 minus theta square. Okay, so this is the maximum overshoot. Or you might be remembering that, say, I have explained that what is actually the maximum overshoot. This deviation is the maximum overshoot. So this is actually your CT max. Okay, this is your 1, and the deviation is CT max minus 1 is the deviation. So that is equal to MP. Okay, now how to find out the percentage? Now I mean, I think I have told the rest. That is, this MP, this is MP, this is actually your MP. Now this MP can be expressed in percentage, will be C of T max, that is a deviation minus 1 from the initial, from the actual value is 1, that into 100. Now when you multiply that by 100, this MP is, or the maximum overshoot is expressed in percentage. To be careful. So the answer that you are going to get, it is not in percentage. When you multiply this by 100, you can convert it into percentage. The actual equation in percentage is C of T max minus 1 divided by 1 into 100. Okay, hope it is clear. I think I have skipped that while we were doing the derivation of this. That is, this MP can also be expressed as percentage. So that means this MP is equal to, so let us evaluate MP to be e raised to minus 0.2 pi divided by root of 1 minus 0.2 square. Since there is no phi, no need of any evaluation. So this will be, you will be getting this as, when you evaluate this is exponential function, right? When you evaluate this, you will get this as 0.526. Okay, now the question is, if it is to be expressed in percentage, MP in percentage is 0.526 into 100. Okay, that is equal to 52.6%, right? Okay, so it is 52.6%. That's the answer. So how to express that in percentage? The actual formula is MP is CT of max minus 1, that divided by the desired value into 100. So this much is the percentage of the shoot from the desired value. So this is 52.6%, we call it like that. Now what is the next what's the next thing that is to be found out? The next thing is to find out the steady state error. Okay, now how will you evaluate the steady state error? Okay, now the last part is the steady state error. There is an addition to this question: steady state error for the ramp input. Okay, this is for, and the steady state error for the ramp input. So this is just the rise time, peak time, and maximum overshoot. From the transfer function you will be able to get this. Now for the ramp input, what is the steady state error? So that is a different question from this. Okay, so we have evaluated this rise time, peak time, and maximum overshoot with respect to unit step. Now they have asked a question called as a steady state error for the ramp input. So what will be the steady state error? So what is actually the error equation? E of s. Now we know that E of s by R of s. Okay, there is an equation which we have studied while we in the last video. That is it is given by 1 by 1 plus gs hs, right? Okay, now we know that this is a unity. The overall transfer function is given like that. So okay, now you can from this, what you need to do is you need to find out E of s, that is R of s into 1 by 1 plus GSHS. Okay, now this R of s is 1 by s square because it's a ramp input. And what is your steady state error? Steady state error is limit s tends to 0 s into E of s. And when you substitute the values for g of s and h of s, considering this system as a unity feedback system, then you will be able to find out that error to be 2 zeta pi by omega n. So this will be 2 into 0.2 divided by omega n is 4 radians per second, right? This is 4 radians per second. So this will be equal to 0.2 divided by 2, or which is equal to 0.1. So this is actually the steady state error. Okay, so the steady state error is given as 2 zeta, and you will be getting this as 2 zeta by omega n. Okay, and you may just study this. The steady state error due to the ramp input is 0.1. Okay. Okay, so here is a block diagram for you. The question is, a control system is shown in this figure, right? Now I will just explain this block diagram. You have a summer with a plus and minus, again another summer, right? So with a 4 by s plus 4 block and a unity feedback, right? Then you have another feedback with the splits as s plus 1.2 and 0.8, which is sum term. So from this you can convert this as a parallel block. This is a canonical form. You can convert this into a single block, right? Now doing these things, I'm not going to into the details. You can do it by yourself. Okay, doing that, you're going to get a graph like this. A block diagram like this. Say that is your R of s is equal to R of s. Then this is plus. This one is minus. So this block, that is s plus 1.2, s plus 1.2 plus 0.8, right? S plus 1.2, s plus 1.2 plus 0.8, 1.2 plus s plus 1.2 plus 0.8, which is s plus 2, right? So you have a block like that, s plus 2, and then this block, this is a bigger block, that is, you can convert this as this, consider this as g of s and h of s as 1. using that canonical equation, you can convert that single block as 4 divided by s into s into s into s plus 4, right? S into s plus 4 plus 4, right? So you can have an equation like this. So you may just check whether you are getting this. So this is the closed loop, or this is the canonical form of this block diagram, right? Canonical form of this block diagram. Okay. Now, then what you need to do is you are asked to find out the transfer function. Now from this, how will you find out the transfer function? Now using C of s to R of s is given by say gs by 1 plus gs hs, right? So what is it? gs is 4 by s plus 4 into this thing, hs is s plus 2. So that what you're going to get is, now after substitution and necessary calculation, you're going to get, you may do that by yourself, it is very simple, s plus 2 into s plus 6. Okay, so this is actually the transfer function, and that's the first part, determine the transfer function. And next is find an expression for the input, for the output, if the input is a step with 2 units. That means this r of s is a step signal. So r of t is a step signal, that is u of t is a step signal. It's a step signal with the step size 2. With the step size 2 means step size 2. That means it is a step input. It's not 1. The amplitude is 2. That's the meaning. So if r of t is equal to 2, what is r of s? R of s will be 2 divided by s. So substituting that this in this equation, you will get the equation as C of s is equal to 2 by s into 4 divided by s plus 2 into s plus 6. Now the thing is very simple, right? So you can convert this as a by s plus b by s plus 2 plus c by s plus 6, right? So you can have that partial fraction resolving. Now after partial fraction resolving, you will get your c of t to be 2 by 3 minus e raised to minus 2t plus 1 by 3 e raised to minus 6t. So this is the answer. Okay, so such kind of problems you will be asked. So this is a very simple question. These are the two questions which I have discussed in this video. Now I'll be giving more of it later. So anyway, you may just work out these. So the important thing is that in this problem, what you need to do is convert it into the canonical form. Use the canonical form to get the transfer function, and look at the question. What is the input for which your output is to be measured? Okay, so it is not necessary that every time you will be asked directly the derivation of c of t. This is an application of that derivation c of t. This c of t we have derived, okay, in our previous video. Okay, so this application can also be asked. So keep that in mind.